All right, so we're taking a look at 7.3, similar polygons. We've talked about similar polygons before. When something is the exact same shape but a different size, we've talked about that as being either an enlargement if it gets bigger. If the representation is bigger, the scale diagram is bigger, it's an enlargement. And if the scale diagram is smaller, it's a reduction. But enlargements and reductions are similar shapes or similar polygons if they have the exact same shape but maybe a different size. So if we have two things that are exact same shape, that means there's corresponding parts of the original and the scale diagram. The angles will be the same. You'll find out all this sort of stuff as we move through the lesson. But similar really means the exact same but different shape. Okay? All right, so a polygon, let's talk about what a polygon is. A polygon is a closed shape. Now a closed shape means that basically all the sides touch, okay, at a single point. Closed shape with straight lines. So we're not talking about curved lines, it's just straight lines. Exactly two sides meet at something called a vertex. So a point where two sides meet, that would be called a vertex. So you see, if there's more than one vertex, we say that those are vertices. So the language is a bit different there, vertex and vertices. Just like axis and axes, more than one axis, on xy axis, x-axis, y-axis. Together, the plural is axes. Okay, so polygon and polygons, when you say, when you refer to something that's more than one, that's the plural form. Sometimes you just add an S. Sometimes the word changes, the suffix, the ending changes a lot. So a vertex and multiple vertices. I'll just write that down because that's good to know in math going forward. So multiple vertices. Like vertices is what it looks like. Okay? Vertices. All right, so let's see there. All right. A regular polygon has equal sides and equal angles. So when we talk about a regular polygon, that means that all of the sides that are represented in the closed shape, all the sides are the exact same length. All right? So here, all of these sides are the exact same. Just to each other. Just out of curiosity, do you guys know what the names of any of these are? The first two would be easy, probably. What's this first one? Triangle. Yeah, it's a triangle. Tri is 3, right? So triangle. What's this one? Square. Yeah, it's a square. If all the sides are equal, truly, then it's a square. Good. What's this side? It's got 5 sides. What's that one called? Yeah, it's pentagon. Very good. Penta is the prefix for 5. And we might talk about this a little bit later, but this will come up in math for the rest of your life. I mean, you'll see this all the time. What about this one? So it's 6 sides. You know what that one's called? Hexagon. Yeah. So hexa is the prefix there. And what about this one? What's it got? 1, 2, 3, 4, 5, 6, 7. Octagon is 8. Like octopus. Yeah. Actually, somebody said septa. Somebody said hepta. Both correct. Both correct. So heptagon is probably the one you'll see most often, but also septa is fine as well. So heptagon or septagon. The world's a big place. People call them different things. Yeah, the naming of these things have been around for a long time. So there's sometimes, like in the metric system as well, there's multiple ways of spelling things, and because it's a global language that we're trying to do here. Okay. All right, so that's great. Let's keep going here. When a polygon is an enlargement or a reduction of another polygon, we say the polygons are similar. So I just explained that off the beginning. Reductions or enlargements are called similar. When two polygons are similar, corresponding angles are, what do you think? Yeah, are equal or the same. That's right. Corresponding means that the angle that's in the same position relative to all of the other aspects of the figure as the original. So for example, if I'm looking at this Well, okay, here, let me draw something for you here. Let's do this one, diamond kind of shape here. That's a bit of a rhombus, I would call that. Let's put another one up there. So if this is an enlargement of this diamond shape here, then this angle right here would correspond to this angle. See, they're corresponding, so they're the same relative to the other aspects of the figure. This is a different angle, and that would be corresponding to that one. Now, it just so happens that opposite angles here would be equal, so it makes that a little trickier to identify. You don't really know if this diamond's been totally spun 180 degrees or not, but in a lot of cases like this example down here, a corresponding angle for 45 would be this one over here, because it's in the same position relative to all of the other angles and sides and aspects of the figure, okay? So corresponding, right? The desk at the front of this classroom on my far left at the front would correspond with the same desk in another classroom that's at the far left at the front where the teacher is at the front there. That's a corresponding desk. Those two are corresponding desks. Does that make sense? Okay. All right. So your left arm and someone else's left arm would be corresponding parts, right? All right. Corresponding sides are, the big fancy word starts with a P. What do you think it is? Yes, thank you. Proportional. Proportional. And we spent a lot of time in the last couple lessons talking about this, didn't we? If they have the same ratios, they are proportional. So if it's 2 to 4, let's say, original to enlargement, and the other one is 3 to 6, and the other one is 8 to 16, those are proportional because you multiply by 2 each time, for each side, okay? So proportional. All right, so the question here is, are these two polygons in the, and I'm going to get rid of this here, are they similar? So we're going to examine whether we think that these two are similar or not. So let me just get rid of some stuff here. Are they similar? Okay, so we're looking for the same sorts of ratios between the side lengths, and we're looking for exact same angles, because the angles are what inform us about the shape. So the angles are what tell us about the shape. If all the angles are all different, then it's not the same shape. Right? If they're all different, this one, all these angles are different from all these angles, it's not the same shape. So this is good that we have 90 and 90 here, and we have a 90 and a 90 here. That's awesome. And then 45 and 45 we mentioned already, and 135 and 135. So that's really, really good that we have all the same angle. Let's check to see if the sides then are proportional. Okay. Now, you can start from either one that you want. I'm going to start from the one on the right. Do you know why? Because I see a 1 here. This side right here is 1 centimeter. And so that's an easy one to figure out, you know, a scale factor, because the corresponding side is 1.5. So what do I have to multiply 1 by to get 1.5? Yeah, 1.5. See how easy that was? So to go from here all the way over to there, I multiply by 1.5. Now, what about going from this one to all the way over to this one, 3? Would I multiply by the same number? So let's check to see if this is true, and you probably don't even need your calculator for this, but we can totally use it. All right, so we'll go to, bring that down just a bit. We'll turn it on. We'll go 2 times 1.5 is 3. That's awesome. Now, if you're doing that in your head, multiplying anything by 1.5 is actually really easy, okay? Multiplying by 1.5, it's the same number plus half of that number. So 2, multiplying by 1, the 1 part would be getting 2, and then the 0.5 part would be half of 2, which is 1. So 2 plus 1 is 3. 10 times 1.5 is 10 plus 5. 26 times, let's go 28 times 1.5 would be 28 plus 14, right? 42, okay? So multiplying by 1.5 is pretty easy. 3 and 4.5, let's see. Well, you've got 3 plus half of 3. That's 3 plus 1.5 is 4.5. Nice. Tough one here, or did I just do this one? No, I did. Yeah, I just did this one. 2.8 times 1.5 is 2.8 plus half of that, which is 1.4. So 2.8 plus 1.4 is 4.2. So all of the sides are corresponding. They have the same scale factor. Okay? So here's the work below. Here's the work below. So let's just check to see if we line up with what you see in your notes package there. So all the corresponding angles are equal to each other. Boom. We did that. That's great. We took corresponding sides. All right. And we went from 1 to 1.5. And we found the scale factor. Awesome. Basically, we did a very similar thing here. We took the smaller one multiplied by the scale factor to see if we got the new number. The smaller one multiplied by the scale factor to see if we got the new number. The other way you could do it is the way they show it here. So corresponding sides, what's the ratio of the corresponding sides? 1.5 divided by 1 is 1.5. 4.2 divided by 2.8 is 1.5. So they checked all of the corresponding sides, wrote them as a ratio, and the same number should show up every time you simplify. Okay? So there's two different ways you could do it. Multiply by the scale factor once you find that out, or just take the ratios of corresponding sides, make sure those ratios are all equal. Okay? When you do this, the little hint here is to be consistent. Make sure that if you're going to do this ratio method, keep the larger one on top always, or keep the smaller one on top always. It just make sure you don't mix them up, right? Okay? So, question?
So would they, so I've seen that we have like something like this to check corresponding sides we do this and we all do like the same answer.
Yeah. If you check the corresponding sides just like they're shown here, then this should always be the same number. They should be proportional. Every side, yeah. If all these numbers are different, or if they're all the same except for one side. See, if one side was out of whack here, I'll say out of whack, that's an old expression if you've heard that before. If one side was a little bit funny, then we truly wouldn't have all the same angles either. So think about this, right? If we had something like this, and then we had something like this, where these sides, have a certain ratio, and these two sides, they don't really follow that ratio. If that's the case, then really this angle and this angle will not be the same, because this is a longer side. It has to fit in there. So the angles wouldn't be the same either. So if the angles are the same, you got a pretty good idea that's going to be proportional. But this is how you check. Okay? Good question. How you guys doing so far? All right? With this? Okay, all scale factors are equal. So corresponding sides are proportional, and all corresponding angles are equal. These figures are similar. And again, similar does not mean sorta, kinda the same. Like, it's similar. Is this what you want for Christmas? It's similar to what I was asking for Christmas. Or, is this your mark on this test? Oh, it's similar. It's not quite this. It's not like that kind of similar. Similar in geometry here means really the exact same shape, just maybe a different size. And truly, they could be the exact same size as well. All right, you got the energy for one more here? We're going to split this lesson up just into two little parts, I imagine. But let's do one more example. So the following figures are similar. Now they're looking at this from a different perspective now. The following figures are similar, so determine the lengths of all the missing sides. Or in this case, they just ask you for two. They ask you for JI and JF. So here and here. Oh, is screen still frozen? Thank you very much. All right. So they've got two figures, and they're asking you for these missing sides. Okay. Well, we know the figures are similar, so we... Wow. Are you all right? That was just your bottle that got damaged? Okay. Whew. Thought a bomb went off over there. We know the figures are similar, so we know that all the corresponding sides are proportional. That means the scale factor for one pair of sides will be the same scale factor for all the pairs of sides. So are we given any sides, any corresponding sides that are given in this question? Are there any that are given? Yeah. It looks like this one, DC on this one, and IH on this one. Do you see how those are corresponding sides? All right. So we can find out what the scale factor is here. So let's take HI, which is this one, IH, divided by CD. So that's 3.6 divided by 2.4. .6 divided by 2.4. Now, what is that as a scale factor? Now, you can get your calculator out, and we'll do that. 3.6 divided by 2.4 is, well, 1.5. Nice. 1.5. Famous scale factor today. So that means that if I took the small measurement and I multiplied 1.5, I should get the bigger measurement. And what you should see is that this ED right here is a corresponding side to IJ or JI. So I need to do 1.8 and do what with it to find this side? I need to multiply by 1.5. Awesome. Okay. So let's see here. So JI then is going to be 1.8 times 1.5 equaling 2.7 when we do that on our calculator. We'll make sure we include our units as well in our answers. And then for JF, okay, I'm given 1.2, so I multiply by 1.5 there. And I get, should be 1.8. So this, 1.8 centimeters. All right. All right, so we know what similar shapes are. The exact same what? The exact same shapes, so they also have the exact same corresponding angles. And the sides for similar shapes are, what's the big word? Proportional to each other. All right. A polygon is a closed figure made of straight lines, right? Closed figure. Here's an open figure, by the way. This would be an open figure that's not closed. There's an open spot. So this would have to kind of bend over here. This would have to bend over here to make an actual triangle, see? So closed means you can't, like, you can't basically drive a car into the parking lot here. This is closed. If it was open, then you could drive a car in. It's open, okay? So you should not be able to drive a car into a closed polygon. Thank you. Yes, that is totally correct. All the gates are closed, okay? All the gates are closed. If a gate is open, it's not closed anymore, right? So think about that, like each side is a gate. You can swing the gate open, it's not closed. Question?
Wait, is there like another way you can find the corresponding side?
Is there another way you can find the corresponding sides of two things? Like, is that what you're saying? Well, here's the thing. Sometimes that's easy to find corresponding sides. Sometimes it's hard. With this example that we just did over here, I'll erase all this stuff. It's oriented the exact same way, right? So everything is, here and here, here and here, here and here. Like it's facing the same way and everything like that. If something was like upside down or flipped around, sometimes it's tough to find the corresponding sides, but you kind of have to think about, okay, what's the angle, side angle maybe, like, that combination, okay? So that's the way you can find the corresponding sides. You have to kind of think about it in your head too, like what's the same part of this other diagram. So sometimes it's easy, sometimes it's hard. I'll admit that, yeah. All right, that's end of part 1.